And then I pulled up, and then I was like,
wait, I did not know you were EE.
Oh yeah, okay, good, very good.
I know you. We definitely.
Yes. Now it's time to hang out with me. Okay, you guys can hang out with your friends whenever you want. Now it's time to hang out with me. I look forward to this 90 minutes every single week. So let's have fun. Okay. Today's lecture, Thomas and I have very mixed opinions about it. On one hand, we think it's some of the coolest material that will cover all semester, especially if you like SAT stuff. On the other hand, it's quite complex. So that is a fair warning. It is quite complex, but I challenge you. This is a challenge. When you start to get confused, don't tune out. I want you to do everything in your power. Use that attention span that has been constantly diminished over time and somehow fight it. And just try to figure out what's going on. If you get confused, raise your hand. Because I want you guys to appreciate this content. So that way, we continue to teach it. Because every time I prepare for this lecture, I'm like, I hate myself for such annoying stuff. But it's cool. Promise? You'll challenge yourself? Yes? Awesome. Robbie.
For a reward for staying concentrated, at the end, can we do another session of ask you any question you want?
Yeah, or maybe I'll do that sometime in the middle of the lecture when I get time. But yeah, we can definitely do that. Okay. Ready? Everyone's ready. Okay, I'm not ready. So here we go. Recap from last week. I forgot to put the pure mem stuff here, so my bad. Whatever. So, last week we talked about trying to build up an algorithm or a procedure that can actually solve the SAT formula. Try to come up with something where we can find a satisfying assignment. The first thing we said was like, okay, what happens if you simply brute force every single possibility of assignments? Like, you try x1 equals true, x2 equals true, so on and so forth. That doesn't work. You try something else. Keep on doing that until you hit a satisfying assignment. That works. The issue we said is that, that's like 2 to the n possibilities. Not great. So instead, we said, okay, what happens? Maybe you remember our search tree from last week, which we'll reference again today. And remember, as you go down the search tree, we're making a decision. Each branch corresponds to a decision, setting a variable to either true or false. And the argument was like, okay, brute force is just checking all of these leaves one by one. If there was some way for us to traverse this tree, and somewhere in the middle of it, we get some indication that some of these leaves aren't worth checking because they're going to give us unsatisfiability, that would speed things up because we would skip over a bunch of leaves. That was kind of the inspiration. And so we introduced something called the splitting rule. Some of this notation might seem a little different from last week. I assure you it's the same, it's just shorthand. And we said, okay, take your formula and continuously, set these variables, set them to true or false. And then we said, if a clause is evaluated to true, remove the clause altogether. If a literal is evaluated to false, remove the literal altogether. Keep on doing this. If our formula is the empty set, or we've removed all of the clauses, then we found a satisfying assignment. Otherwise, if we have an empty clause in our formula, we've made a mistake because everything in that clause is false. So if we made a mistake, we have to backtrack. We have to undo a decision. That's equivalent to coming down this search tree and saying, hey, we've made a mistake, let's go up and explore somewhere else. This is all from last week. Any concerns about this? Because this is going to inspire what we do today. 9, 10, 14, 16. Cool. Here we go. So, maybe it's worth thinking how you would go about implementing a SAT solver. And so here's just an idea. Maybe you choose to do this, maybe you don't. But you could visualize a clause as a doubly linked list, where these orange thingies are like your actually doubly linked list. And each orange thingy represents a clause. So the value of this node is a pointer to another doubly linked list. And that doubly linked list represents a clause. Alright, so then the second item of your linked list is a pointer to your second clause, so on and so forth. Just one way of potentially visualizing or implementing this. And why would we choose to use a doubly linked list? Because when you go ahead and do the splitting rule, which requires removing these clauses and removing literals, it's pretty easy to delete stuff from doubly linked lists. For example, if we want to evaluate phi given x2 equals false, this not x2 evaluates to true. So the splitting rule tells us, let's remove this clause altogether. And in the implementation, well, that's just a matter of rerouting the pointers from before and afterwards. Pretty simple operation. And again, with x2 equal to false, in this clause, splitting rule tells us we have to remove this literal because it evaluates to false. So removing a literal, again, we're just rerouting the pointers. Just an idea of how you would implement this. I don't know why. There is a point to all of this, but I'm skipping it this semester, so oh well. It's just here to think about. Okay. Continuing to think about implementation, we now know how to remove the clauses. We now know how to remove the literals. We need to know how to backtrack, right? That occurs somewhere here, but it helps more visually, right? As you go down the search tree, we reach a point that's no good. We have to backtrack. And we detect backtracking, that we need to backtrack, when we have an empty clause. Right? That signals we've made a mistake, we have an empty clause. And in this current doubly linked list implementation, that kind of requires going through all of these clauses one by one and checking if it's empty, which can be a little bit time consuming. But again, this is an implementation thing to think about, probably.
Why are you recommending that we would use a doubly linked list versus just like an array list or whatever?
Doubly linked list instead of what?
Like an array list.
An array list? You could use that. This is one suggestion. The reason why I chose this one is because to actually perform the deletion is like O of 1. Some other data structures you use with like lists and stuff, when you delete an element, sometimes things shift down, it's more time complexity. This is just one option, so you could choose an array list or something like that. Okay, so this is quite important. Like visually what's happening here is we're conducting the algorithm, which is equivalent to going in this search tree. And we're at some intermediary point here. I'll just call this like phi, and this is phi given xk equals true, for example. So if we reach here, and we realize we've made a mistake, this requires us checking every single clause to determine if it's empty. That's pretty expensive. That's one issue. The second issue is when we backtrack, we need to have the formula from above. We can't just use this formula and bring it up here because we've deleted stuff in this process right here. So we need to make sure at these nodes here, maybe I should come up with a different here. At these nodes here, we're storing the formula that exists at that point, and then computing it downwards. So what's the issue with what I just said about storing a formula at these intermediary nodes? What's the problem with that? Same hands every week.
Is it just that you have to store like you have to basically make a value for like a deep copy at every single thing?
Yeah. So what's the issue?
Well, then that's it's slow to make a deep copy.
Yeah, not only is it slow, but when we think about the space complexity of all of this, it's not great, right? We're dealing with an exponential search tree, and if we're storing a formula at every single node, it's a lot of space.
Well, couldn't we just delete the ones from like Because like when we go up the tree, we don't need the ones from those leaves that we left anymore, so we can just delete them as we go. Then we only need like height at any time, right?
Yeah. A little bit more overhead, but that's okay too. Okay. 2 issues that we're kind of facing. One, detecting empty clauses is time consuming. Like, I mean, it is linear time, but if you're doing that every single time for all of these intermediary nodes, that adds up. And then second, smaller issue is like the space complexity nonsense, but we won't worry about that too much. So we need a way of solving it. It's figuring this out. And the way we'll do this is by kind of not doing whatever I just said. So we're actually not going to make a copy of this formula and pass it down, and we're just not going to do the splitting rule of removing clauses and literals, which is like, why? I just spent so much time in class explaining to you the splitting rule, and now I'm like, we're not going to use it. And I don't have a good answer to that question. So instead, I'll just present you with a different procedure, a different way of doing things. That'll be nice. And here's our key observation that'll inspire this new method of doing things. And that's, we must only backtrack once a clause has become empty after the splitting rule has been applied. This is equivalent to saying we must backtrack once we make a mistake. And the mistake is when we have an empty clause. Well, the only time we have a formula, we make a decision, and this now has an empty clause in it, is if here we had a clause that looked like this. This clause must appear in this formula in order for this evaluation to have an empty clause. And this follows directly from the splitting rule, right? We remove literals that evaluate to false. For us to have an empty clause here and not have one here, we must have removed a literal from a clause to make it empty, and the only way that happens is if we have a clause with a single literal in it. Right? Yes? Remember Thomas, if you get confused, raise your hand. We're not even at the hard part yet. This is still the easy stuff. This was supposed to be covered last lecture. Okay, cool, fine, very well. So this introduces the one-watch literal scheme. And this is saying that, well, okay, a clause can only become empty if it has just one unassigned literal remaining. Exactly what I said right here. And so, ideally, as we traverse down an edge here, we only need to pay attention to clauses that look like that, because those are the only ones that can possibly become empty when we make this decision. And so that's exactly what we're going to do. Every single clause of our formula is going to keep an eye on a single literal within the clause. And it's going to maintain this invariant, that if the literal is evaluated to true, then hooray, our entire clause is evaluated to true. We don't really care. That's good news for us. If the literal is evaluated to false, we're going to simply watch another. And I know it doesn't make sense. What does watch mean? We'll see the example in just a moment. But this is all that's going to happen. Let me just show you the example. Here's a formula. The yellow means we are watching that literal. So every single clause here has an eye on exactly one literal within the clause. And we're just going to proceed with our normal process of solving, the SAT problem. We choose a variable and make a decision, maybe set it equal to true. But now, some of the things that are being watched, in particular clause 1 and clause 2, the literal that they're watching has become false. And according to our invariant, it says, if it becomes false, watch another. So all we're going to do with this schema is watch something else. Okay, fine. We're just going to continue the procedure. We haven't made a mistake yet, so we just choose another variable, right? We're following this, essentially. We don't have the empty set, we don't have an empty clause, so let's choose a new variable. Okay? I choose 2. Set it equal to true. This clause becomes satisfied. These two, I don't know why I'm not in presentation mode. These two don't have anything to do, like the thing that they're watching hasn't been affected yet. But clause 1, the thing that it's watching has become false. And so the invariant says, if your thing becomes false, watch something else. But clause 1 can't watch anything anymore. That's exactly equivalent to this case. We had essentially just one literal left because we ignored this not 1 in the first decision. We were left with this, which is equivalent to that right there. Since we can't watch anything anymore, that tells us that's our new conflict. So before, we said we had a conflict when we have an empty clause. Now we're saying we have a conflict when one of our clauses can't watch another literal. It's essentially the same thing. Like, they're essentially the same thing. It's just now we're visualizing things a little bit different. Okay, so it's a conflict, and just as we do over here, we backtrack, right? We need to undo the decision. So we undo that decision, set it equal to false. This clause is satisfied. This one is set to false. We have to watch something new. So we do that. We don't have a conflict. Make a new decision. Uh-oh, what happens here? Shout it out.
There's no more.
Thank you. Well, what does that mean, though? Yes, conflict, backtrack, right? We can't watch anything else. It's an empty clause. Backtrack. And then, so on and so forth. I don't know what's happening. You keep watching things, and then, okay, here we're at 5. Set it to true. Oh, that's a conflict because we can't watch anything else. Backtrack. There. It's the same thing as before. It's just kind of the way we do. We're not doing the splitting rule anymore. We're not removing things. We're just keeping an eye on things.
How do you know which ones you've watched already? And like when to move on to the next one?
I'll answer the second question. How do you know when to move on from something?
Oh, okay, wait. That we know.
becomes false.
But like, yeah.
How do you keep track of what you've already watched? Is something that you'll think about when you do homework too.
Awesome.
Other questions regarding one watch? Yes.
When we pick the first literal to watch, is it we just randomly pick a variable, or is there any a method to it?
Let's say we're going to do it kind of numerically, like as we've been doing it. Like choose 1 first, then 2 first, so on and so forth. Yes. Okay. That's one question. Okay. Quick exercise for you guys to think about. I'll give you about 17.5 seconds to work on it. I want you to find a satisfying assignment for this formula, and you can talk to your neighbors. Shoot, did I mess something up? Yeah. Enjoy. Okay, good. What have we come up with? Even if it's a partial assignment, what have we said? Fine, Jesse. No, it's just it would be so nice if other people raised their hands, but go ahead, Jesse.
We got x3 to be true,
Mm-hmm.
x1 to be false,
Mm-hmm.
x4 to be true.
Cool. And I don't really care about the rest. Why those first two? Why x3 equal to true? Why was that the first thing you said?
Well, if there's a clause with only one item, then our hand is forced. Like,
Okay.
we just only resolve that one. And then that leaves the not x1 and not x3 clause with functionally only one variable, so we should also look at that. And then from there, it's kind of vibes, but
Beautiful. That's exactly what I wanted you to say, so thank you. This seems like such a simple observation, but this is insanely important to speeding up our stat solver. The observation is if we have a clause with just one literal in it, we have to satisfy that clause, so make sure that literal or whatever is in there evaluates to true. So Jesse saw that and he said, okay, x3 has to be equal to true. But then, the second, even better observation is that, well, wait a second. If x3 equals true, and I look at this clause right here, well, this second value is now equal to false because I set x3 equal to true. So that means I have to set x1 equal to false. Right? So no matter what satisfying assignment you come up with, you have to set x3 to true, and you have to set x1 to false. Hopefully this is somewhat intuitive. We need every clause to be satisfied, so if you see one thing in it, well, satisfy that guy. So this lends itself to something called unit propagation. And the idea is kind of exactly what we said. If you see something called a unit clause, and we define a unit clause to be a clause with one literal in it, like this, then satisfy that clause. Set xk equal to false, or set x3 to equal to true. Or, you know, after doing some previous computations, this becomes unit, set x1 equal to false. Us as humans, we know these things, these seem intuitive to us. Our solver doesn't know that yet. So we have to tell our solver, hey, actually, you know, kind of do this. And so, everything we've come up with so far, from backtracking to the one-watched literal schema to now unit propagation, were the ideas that were come up with by these four people, Davis, Cunningham, Logan, and Loveland. Maybe some of these names ring a bell. In the wonderful year 1962, great year actually, I remember it vividly, and they came up with something called the DPLL algorithm, which is just whatever we just talked about. I'll show it on the next slide. And this is still like the basis of a lot of the state-of-the-art stat solvers to this day. And so it looks like this. Look at this, and you might be like, whoa. But look at this. This is what we said last week. This is what we're saying this week. It's the exact same thing, except for these two lines right here, where if phi contains a unit clause, then set the unit clause to be true in such a fashion. That is all that's happened. We good? We not good?
So that's literally the only speed up.
That's not the only speed up, but that is one of the most important speed ups that came about. So let's run through an example.
Wait, can you go back for one tiny second?
Happily.
I can't very fast. Thank you.
Remember, everything will be posted on the website too.
All right, sorry.
No, don't apologize, man. You're learning. Are you gonna apologize to me for learning stuff? Come on. That's not me. Okay, other questions? Yes.
Is it like a good idea to, I guess, like pick the smallest clause first every time, or like how does pick variable work?
Pick variable just means find any unassigned variable and set it equal to true or false.
And okay, maybe this question was asked earlier, but is there a good way of picking? Like, have we defined one yet?
No.
Okay.
You can, for now, you can assume that we're just choosing them like numerically, x1 first, x2 first. You could do other things. It turns out that it's very like formula dependent what is best. So if you come up with a procedure, you can probably find a counterexample of like, oh, this formula, the procedure works really poorly on. So for now, we'll just assume we're doing it in order.
Is there like there's definitely more optimal pick variable, right?
That's kind of what I just said.
Okay.
But yes, we're just not going to talk about it.
What's wrong with like the idea of taking the like one of the clauses that have like the minimum number of
Yeah.
literals?
That could work. However, you do that, but then there's a lot of clauses. So the decisions you make early on, even though you made the easier ones first, there's no guarantee that that means that it's good for the entire formula. I'm talking kind of abstractly here. It's unsatisfying. Oh, unsatisfying. But it's the truth. Okay, example, DPLL. This is going to be in the comfort zone. So we have nothing, choose a variable, assign it. Okay? These two have become satisfied because we see the positive one here. But now DPLL says, hey, we have found a unit clause, right? Because this is left over. Let us satisfy this guy. So that says, oh gosh, set true to false, right? Because the first clause was a unit clause. I know you guys have hands, I know your question, don't worry about it. I'll get to it in a minute, okay? So we do that, but oh no, that's a conflict, right? We have an empty clause, so to speak. What should we do next? What is our next assignment?
Like 2 to true, like backtrack and set 2 to true.
Almost. We would do this if we were going normal backtracking. But we're going to jump all the way up to 1 and set it to false. I'm thankful you said set 2 to true, because this will allow me to show the point. The reason why we're not setting 2 to true is because under this decision of 1 to true, in this space right here, this clause can only be satisfied if 2 is set to false. And so unit propagation tells us we have to set this to false. Ignore what's happening here. Ignore what's happening in the second clause. The first clause says, no matter under this condition, we have to set 2 to false. So because of unit propagation, we're going to say, okay, if we've reached a conflict, we're not even going to try 2 to true, because the first clause already told us we can't do that. So we jump up to 1, being set to false. Now these two are satisfied, these two are unsatisfied. Choose a new variable, set it to true. This clause is now satisfied. This one is now a unit clause. Unit propagation says, hey, we have a unit clause, satisfy this. So what should the last decision we make be?
3 true.
3 to true. Exactly. We found our satisfying assignment. That's just DPLL in action. People who had questions before, you still have a question? No? Right.
How do you know whether it's a unit clause if you can only watch one at a time?
Good question. I'll come back to that in just a moment. Good question.
Oh, I was gonna ask if you could go back to like the slide where we decided to jump up to the 1.
Yeah, so we were here,
Yeah.
and then jump up to 1.
We go back. Wait, so one more back. So like right here, I guess we have 2 unit clauses. Why doesn't the algorithm first, like I guess, try to set one of them to true, and then go back, or is that?
It's essentially the same thing here. Like,
Or did you like skip steps?
well, no, actually, we're just saying if we have a unit clause, which we do. In this case, we'll look at the first clause.
Yeah.
Unit propagation tells us set 2 to false.
Yeah.
It just so happens that we have another clause that's unit.
Mm-hmm.
But unit propagation just says if you have a unit clause, find one of them and follow the rule.
Yeah. So so like in between that, do we set like 2 to false at some point? And then,
Well, right there.
oh yeah. Yes, that's my bad.
Okay. Back to Robbie's question. How do we detect a unit clause if we're only watching one thing? Watch 2 things. Like, there's a lot of words here. I'm just going to show you this picture right here. All you do is watch 2 things. If something gets evaluated to false, as is here when 1 is equal to true, watch something else. So 2 stays, but now this guy is watching that. And then if something else is set to false, we have to move this guy. It has nothing else to watch, but we still have one leftover thing being watched. Henceforth, it is a unit clause. It's a little bit annoying to understand, but I'm not going to spend too much time on this because there's a lot more stuff to talk about and I don't have enough time. But you just watch 2 things. It's the same thing as when you watch 2 things. Okay. All right. I'll pause here if there are any lingering questions. Yes.
Wait, so how do you keep track of the empty clause? Like instead of removing the entire clause, what do you do?
One watch literal, Schema.
One. Okay.
Yes. And then if your clause can't watch something else, that means it's empty.
Okay.
Other questions? Okay. This was supposed to be the end of last lecture. So that's why I said last lecture that was, oh gosh, I'm really bad with time. So we have to do all of today's lecture in an hour. Less than an hour. It's not going to be fun for me. It'll be fun. Okay. So we're taking a step forward in time. What we just talked about, DPLL, that was 1960. That was before we set foot on the moon. How embarrassing is that? Now we're stepping forward at least 2 decades into the future. So some of the stuff we'll talk about was introduced in the 80s, 90s. There's more stuff that's been developed. I'm not going to talk about that, but these are some of the more modern things that have come about. So, one thing that may be a pain point right now is the way that we're backtracking. That when we find a conflict, when we've realized we've made a mistake right here, we backtrack up 1 level. And then we keep on going. Which is fine, you know, we solved the problem, but remember, we're trying to solve this fast, right? We want to be as good as we can. And so the issue, if you can even call it an issue, is that we might reach conflicts or contradictions caused by the same underlying reason over and over again. To highlight this point, example, as always, here's a formula. Let us do DPLM. Choose a variable, set it to true. We have no issue, so choose another variable, set it to true. Now we have a unit clause. DPLL says, hey, set 4 equal to true. But in doing so, we now have a conflict in our last clause. This is an empty clause. We have nothing left to watch. So we backtrack. In this case, we won't backtrack here because this decision was via unit propagation. There's no point in checking it equal to false. So we backtrack up there. Set it equal to false. DPLL says, hey, a unit clause, set 4 equal to true. In doing so, we have a conflict there. It's another empty clause. So we backtrack. Again, we're not going to backtrack to here because this was unit propagation. We've already exhausted all possibilities here. So we go all the way back up to 1 and continue our search with setting 1 equal to false. That's a lot of wasted time, right? We just explored this entire, well, not the entire subtree, but a big subtree for no reason whatsoever, right? If we had just made this decision first, we'd be on our merry way. And you know, this is a deliberately chosen formula, because when you set 1 equal to true, this is an unsatisfiable subformula. No matter what you do, that'll never evaluate to true. And so, if only there was a way for us to detect when we reach a conflict, you know, that, like, hey, this decision we made very early on, like if somehow when we reached here, if somehow we were able to say that maybe this decision was really bad, and we just immediately went back and set 1 to false, that would save us a lot of time, right? We'd avoid making all of these additional searches. Right? That's the inspiration for today. How are we going to be able to go back to a decision that we made that was bad? You might be like, well, what even is a bad decision? We're gonna figure that out. So this is something called a back jumping. Instead of backtracking up 1 level, we're going to try to back jump up many levels. And so this is the idea right here. Instead of backtracking 1 level up, we are going to back jump to an important decision. We're going to go back to that variable 1 and set that equal to false. This is the question we have to tackle. How do we know what is an important decision? And this, ideally, shouldn't set well in your head. Because this is such a qualitative question. What is an important decision? What is an important decision?
It's present in many classes.
Hmm?
The literal variable is present in many classes.
Okay, maybe. Maybe.
Deciding to eat breakfast.
Agreed. Do you eat breakfast?
I usually just drink a fair amount.
So no.
Sometimes a banana.
So no.
Yeah. Oh yeah. No.
That counts. That counts.
I feel like causes a lot of conflicts.
It causes a lot of conflicts. Large number of conflicts. Okay, maybe. Good. I won't tell you the answer right now because we have to build up to it. So, in building up to all of this, we need to, of course, learn more vocabulary, which is, the most fun thing in the world. But before we get to the vocabulary, we just talked about DPL, like literally 10 minutes ago. So this question, ideally everyone's hand should be in the air. What are the different ways in which variables get assigned in DPLL? In other words, what are the different ways in which we let xk equal true or xk equal false? There are 3 that I can think of. And you can reference the code here or your brain. Everyone should know them. I just talked about 10 minutes ago. Yes?
The literal is in a unit clause, it should be assigned true.
Beautiful. We'll call that by unit propagation. Right? If we find a unit clause, well, we set it in a certain way. Good, that's 1. 2 more.
Just like randomly choosing like one thing if it's true or false.
Yeah, and
your
we'll call it like
decision
the selection step. Right, like right here, when we pick an unassigned variable and then set it equal to true or false, we'll call this the selection step. Actually, I'm going to call it the decision step. What else? What's the last one? If your hand is up, just call it out because I don't want to look around. Okay, that's no one knows. What's the last one? Yes.
Like backtracking?
Back. Cool. Those are the 3 ways in which a literal or like a variable gets assigned. So, for terminology, we're going to say that a decision refers to any time our algorithm arbitrarily assigns a variable without being forced to do so. In other words, the decision step occurs like pretty much here and like there. When we have no issues, no conflicts, and we just need to choose a variable and decide what to set it equal to. That is something we'll call a decision. When we assign variables via unit propagation or via backtracking, that we will not call a decision. Okay? Those are not decisions. I might use the word, it's an assignment that's occurred. That's what a decision is. All assignments implied by the ith decision are said to be on the ith decision level. Okay, before I say that. Can someone tell me what is the definition of a decision? Okay, not everyone's hands in the air. All right, so we're going to define a decision, once this loads, to be any time our algorithm arbitrarily assigns a variable without being forced to do so. In other words, the decision step right here, unit propagation and backtracking, will not be called decisions. All right, can someone tell me what a decision is? Okay, not everyone's hands in the air. So we're going to define a decision to be any time our algorithm arbitrarily assigns a variable without being forced to do so. In other words, right here and there. So unit propagation and backtracking will not be decisions. Little love of God. Can someone tell me what a decision is? Raise your hand, please. Tell me what's a decision.
Anytime our algorithm arbitrarily assigns a variable without being forced to do so.
Hurrah, let's give a round of applause. Oh my goodness. Good job, we now know what a decision is. Great. Now I can use that word confidently. So anytime we make a decision, which is... Let's just say it out loud.
Anytime our algorithm arbitrarily assigns a variable without
Brilliant. Anytime we make a decision, we will create something called a decision level. Whatever. This is just a way of organizing our thoughts that, you know, this first decision we make here, x1 equals true, this occurs at decision level 1. Maybe we do something else and that occurs at decision level 2 if we make a decision. If a variable gets assigned via unit propagation or backtracking, that's going to occur at the same decision level. So for example, suppose this is our formula, a single clause. If we were to follow DPLL, you would make a decision, so choose a variable, and set it in some way. So this occurs at decision level 1. Okay. Okay, let me make this false actually. Alright. Our formula is not yet satisfied, so we choose a different variable and make a decision. So maybe I set x2 equal to true. This is at a new decision level. So now these two are both evaluated to false. But now unit propagation says, hey, x3 should be set to true. And since this occurs via unit propagation, where's my other marker? What's in my pocket? Wow. This is occurring by unit propagation. We're going to say that this also occurs at the same decision level. I'll move out of the way so I can see. Okay? So unit propagation and eventually backtracking occurs at the same decision. Yeah, Robbie.
Wait, I thought you said they weren't decisions, though.
Yes, but they occur at a assignments always have some sort of associated decision level. The number of the decision level is dictated by the decisions we make. Okay. We'll see a visualization, maybe that'll clear things up. Okay, let me check what slide I'm on. 58. Okay, that's not that bad actually. Alright. Very well. Okay, now remember. Our goal is to back jump. Right? That's the thing I showed a few slides ago. We want to be able to back jump. Keep that in the back of your head for the next however long this takes. All of this will build up to us being able to back jump. So, this is a key observation. It's in green, so it's probably worth knowing. When we backtrack, all assignments made at the current decision level get unassigned. So who can tell me what was in that green box? Okay, not everyone's hands in the air. So when we backtrack, all assignments made at the current decision level get unassigned. So who can tell me what was in the green box? One more time, I think. So when we backtrack, all assignments made at the current decision level get unassigned. So who can tell me what was in the green box? Raise your hand. Now, before someone tells me what was in the green box, who's lying right now? Who doesn't know what was in the green box? Right. Honesty is better than anything else, so. Okay, someone tell me what was in the green box. Actually, as a collective, on three, let's all shout it out. 1, 2, 3.
When we backtrack, all decisions at the current level unassigned.
Close. Some people actually made a mistake. Some people said, when we backtrack, all decisions made at the current decision level get unassigned. That is unfortunately incorrect, because as Berto explained, what a decision was, what's a decision?
Whenever we arbitrarily assign variable.
Exactly, right? That is what we said a decision was, and an assignment is when any of these three things happen. So there's a subtlety there. It's just important to be aware of what's going on. Great question.
I don't get the difference between a decision and an assignment.
Okay, this is our formula.
Yes.
We're going to execute DPLL together.
Sure.
Or essentially this plus the unit propagation step. Okay? Step 1, we have nothing. Neither of the base cases hit. So we choose an unassigned variable. X1, let's set it equal to false. That's the decision we've made.
Sure.
This is a decision. We're arbitrarily selecting a variable and giving it a value.
So it's like the either true or false decision?
That's here, and yes, like this underlined part here, or that if you choose to be equal to false. It's not easy to parallel these two. It's essentially when we get here and we need to go down a level, which direction do we go down? Either we set it equal to true, or we set it equal to false.
Makes sense. But an assignment, would that be like x1 is this, x2 is that, x3 is that?
No. So this is a decision.
Uh-huh.
So this now evaluates to false.
Yeah.
We have nothing else to do but to choose another variable and assign it. So we will choose x2, and maybe we choose to set it equal to true.
Sure.
That is a decision. Now both of these are false. We have a unit clause now. That's the only thing left.
It's forced to be true.
Unit propagation forces this to be equal to true. So since this is set by unit propagation, we'll call that an assignment. A decision is only when we select something and we're like, hey, let's set it equal to false. It's not a forced action.
You said the assignment is like all three, right?
Yes, so this is a decision, and all of these are
Assignment.
the word assignment applies to, or let's draw it this way. So this is our decision space, and this only contains number 2 here, and our assignment space contains 1 and 3 and 2. So all are classified as assignments, but only 2 can be called a decision, can also be called an assignment. That's fine. Very well. Okay. When we backtrack, all assignments made at the current decision level get unassigned. Let's see it. So we have a formula. We're going to execute DPLL. We choose a variable, set it equal to true. This is a decision that we're making. There should be a slide with no colors, like at the very start, but oh well. We're making this decision. DPLL says, hey, we have a unit clause. Set that equal to false. So we do this. But setting x2 equal to false, this is an assignment. It is a result of unit propagation. So we would say that setting 1 to true, this occurred at our first decision level, and this was a decision. setting 2 to false was an assignment by unit propagation also at decision level 1. The decision level only increases when we make a decision. That's why it's called a decision level. Okay? We have a conflict, so we must backtrack. And what was in the green box?
All the stuff at the current decision level.
All assignments.
Oh, all assignments
At the current
at the
decision
current
level.
decision level get unassigned. Exactly. We have to backtrack.
Stuff.
So everything that was assigned during the first decision level will get unassigned. So 2 gets unassigned. 1 will also get unassigned. Oh, wait, I went backwards. Sorry. 1 gets unassigned, and then we make a new decision. Right? So I guess you can call this decision level 2, or whatever you want. But we've made a new decision. The key thing to note is that 2 got unassigned, 1 did 2, and then we made our next decision. Questions? Yes.
If decisions are like arbitrary, how do you know what decisions you've already made and like know you have to go like 1 false next? Like what if like I did like 1 true and then I did some other things that were arbitrary and I came back and did 1 true again, would that be allowed or are we tracking the arbitrary, the very next?
Ideally, you should have some sort of bookkeeping that I've already decided 1 should be true. I've done my search, like I've explored the entire subtree and it's unfruitful. Therefore, I will make the other decision. It's kind of handled in this code here. This is saying I'm going to search the entire subtree where we set it equal to true. That's exploring the entire subtree when we set it equal to false. So it's kind of handled for you already. But yeah, you keep good bookkeeping. Other questions? Okay. Our goal is to back jump. And I just taught you about decisions and decision levels. In fact, let me check something really quick. Let me check something really quick. Yeah. Okay. Here we go. So, yeah, so I was on the train here and I was like, man, this lecture is so confusing. So let's try to flowchart our way through this. At the start of the lecture, I said we want to be able to back jump. And thus far, the only things we've discussed is where do we want to back jump to an important decision level, or to an important decision we made. We'll just say it's synonymous. And we've raised the question of what is an important level, like where do we know to back jump to? We haven't quite answered that, but I basically said that, like, you know, something where our decision actually contributed to the conflict. Think about that, the formula which was like 1 or 2, and then not 1 or 3 or 4, and then 3 or not 4, not 1 or not 3 or 4. Right? We said that this setting 1 to true, that was an important decision that actually contributed to the conflict. We've answered that part thus far. It connects to more stuff. We'll get there eventually. We also discussed why do we want to back jump? To avoid the repeated work and like the pointless subtrees that have no point to explore. So that's where we are thus far. Let's see what's below this. Ah, yes, okay. Now we're going to try to answer the question of how do I find those all-important decisions? Implication. A brand new concept. Lots of words here. Don't read these words. Don't read these words. Look at me. Look at me. All eyes on me. Wow, so much attention. Feels so long. All we're going to do is we're going to do DPLL, as we've been doing many times before. But as we do DPLL, we're going to construct a graph. So we are going to go through the procedure of assigning things, whatever, and for whatever reason, we're going to draw a graph. Now it's going to look like something like this. And then later on, I'll tell you why we're constructing the graph. The graph will give us good information. Okay, so you can stop looking at me if you want, or you can keep looking at me. No problem, either way. So, our graph is going to contain vertices that look like that look like that. Let's do it like this. Our vertices will look at like x at t. And this is equivalent to saying we are setting x equal to true at decision level t. And I could have not x at t, that would mean setting x equal to false. Those are what our vertices are going to look like. Something like that. So, not y at t2 maybe. And we'll have edges that point, I'll call it colloquially u and v. I'll have an edge u to v if the assignment that is being dictated by the vertex u, in this case setting x equal to true, if that eventually implies us making this assignment here of y set to false, if this assignment can be explained by this assignment, then we draw an edge. Abstract, yes, I know. Visualization always helps, at least for me. But do we kind of get what the vertices look like? Do we kind of get what the edges look like? Remember, if you're confused, hand should be elevated. Probably.
What is time?
What is time? Anytime we create a new vertex, we will add on to our timestamp. So this is the first vertex we create. This occurs at time t equals 1. I'm going to call this decision level instead. Here we create a new vertex. It's created when we make this assignment. This occurs at maybe t equals 2. Anytime we create a vertex, we increase the timestamp by 1. Yes.
Can you go through an example of making one of these tags?
Absolutely. You think I just show this to you and be like, yeah, figure it out yourself? No, man, we're going to walk through an example. Come on. You know what I'm like. Other questions? Yeah.
So there's a edge between u and v if they're on the same decision level?
No. They can be on different decision levels. Let's go through the example. Here we go. Again, all we're doing is we're going to do DPLL. We're just going to construct a graph off to the side. So, new formula. We conduct DPLL. First, we choose a variable given an assignment. So maybe I choose to set variable 1 equal to true. This is the first decision I'm making. So we're at decision level 1. And it's the first vertex I'm creating. So time t equals 1. We've created a vertex. That's all we've done. We have no issues. We don't need to backtrack or change anything. So we just choose another variable and make a decision. So in this case, maybe I set 2 equal to true. This is a new decision. So my decision level increases by 1. We're now at decision level 2. We've created a new vertex, so time increases. You don't need to worry about time right now. It'll come into play later. So for now, make sure you understand the interior of the vertex. But that's that. We have no conflict, nothing else. We make another decision. Maybe I now set 3 equal to true. This is a new decision level. Decision level 3. Increase the time. But now, DPLL tells us, hey, you have a unit clause up here. You have to set 4 equal to false. So, when I click the right arrow, what vertex should appear? What should the interior of the vertex look like? Yes?
Should be like negating 4 at 3.
Negated 4 at 3. Why?
Because it's not a new decision level, happening because of decision level number 2.
High five. Good work. Not 4, at 3. It's via unit propagation. It's an assignment, not a decision. But now we have these edges here. So why do we have these edges? These edges exist because we make this assignment, not 4 at 3. The reason why we're making this assignment is because earlier on, we set 2 equal to true, which made this bad. Hence, we have an arrow. This explains that. And because we also set 3 equal to true. This explains why we're making this assignment later on. So we have these edges, saying, kind of giving explainability. That since we made these 2 decisions / assignments early on, that explains why we're making this assignment later.
So it's only the ones that are within the clause of one of the non-decision assignments?
Yes. Okay. Yeah.
So we're only pointing arrows whenever we make assignments due to some decision.
Yes. Okay. Let's continue with the example. So, okay, we've set 4 to false. We don't have any unit clauses. We don't have any conflicts. So now we have to make a new decision. We have to arbitrarily select something and set it in some way. So maybe I select 5, set it equal to true. We're at a new decision level. We've made a new decision. So that's the new vertex. Someone tell me what should the next vertex be? Only the vertex.
6 to false. 6 to false.
6 to false at?
T equals 6.
At t equals 6, but what's after the at symbol?
Oh,
what decision
at
level?
4.
At 4, perfect. Unit propagation tells us 6 has to be false. We're still at decision level 4. What will the edges be? Probably.
3 and 5?
Perfect. Not 6 at 4, because unit propagation. This is explained by us setting 3 to true and 5 to true earlier on. And then we proceed. We have a unit clause here, so we have to set 7 to true. So it should say 7 at decision level 4. Again, this is a consequence of unit propagation. We haven't made a new decision. This is there. This is explained by this clause, 4 to false, 6 to false. We have another unit clause here. So we set 8 to false. That also occurs at decision level 4, explained by 7. We have another unit clause. So we set 9 to false. At decision level 4, we're still at the same decision level. We haven't made a new decision. This is explained by 1 to true, 7 to true. Now we have a conflict. So for a conflict, we will introduce a conflict vertex and give edges the exact same way. We have a conflict because 1 is true, 9 is false, 8 is false. This is how you construct a decision grid. I want to make sure this sits well. You understand? Okay, so the goal was backtracking, and now we have constructed an implication graph.
Wait, so the edges to the conflict, like vertex, are just these things in the clause?
Okay. The goal is backtracking. But now we have an implication graph. You're probably like, what's going on? Like, how is this going to tell us about backjumping? So we're going to build the bridge of how this gives us information that we can use to backjump. More definitions. we'll call a conflict set to be a set of assignments that collectively imply a conflict. No, I'm not going to do that. I'll just tell you. So, a conflict set is a set of assignments that collectively imply that we have a conflict. So, as an example, maybe this is our formula. An example of a conflict set would be x1 equals false, x2 equals true. It is a subset of assignments that no matter what happens, if we have x1 equal to false and x2 equal to true, we will never satisfy the formula. Hopefully this makes sense, because they're not going to satisfy the first clause. No matter what else we do, we'll never satisfy the formula. So a conflict set is a collection that always means we'll have a conflict. And now, this is a bad example because it's a very shallow conflict set. I just looked at the first clause and negated both of those. But sometimes, in fact, often, conflict sets can be much deeper, something that we just can't see by inspection. Why is this good for us? If we do DPLL, and we somehow detect we have a conflict set, we're in our search tree, maybe we're here, and maybe we have x1 equal to false, maybe we have x2 equal to true, x3 equal to false, so on and so forth, some sort of partial assignment here. And if we can say that, hey, some of our assignments there contribute to a conflict set, that tells us we're in trouble. No matter what we keep on doing, we're just going to keep on running into conflicts. In other words, if we ever detect a conflict set, something like this, ideally we tell our solver, never ever set x1 to false and x2 to true again, because you're going to run into issues. So conflict set is this set that basically tells us you're going to fail no matter what. Kind of think of it like backtracking, where we detected we were in a conflict when we had an empty clause. Now we detect we have an error when we find a conflict set, essentially.
Yeah, I was going to ask, what's the difference between last class's empty clause and then conflict set here?
Conflict sets can be much deeper, meaning the conflict set might have one variable here and then something here, something else. So it'll come together soon. Just for the sake of time, I have to power through this lecture, so we'll save questions for later. Okay. It turns out our implication graph can give us a conflict set really easily. And the way you do it is by cutting your graph. So for example, this is the graph that we came up with. All you need to do is draw a line such that, this is important, all of your decision vertices, these green vertices are specifically when we made the decision, all of the green vertices, decision vertices, are on one side, and all the conflict vertex is on the right side. So no matter what color line you look at, the green vertices are all on one side, and the conflict is on the other side. But all you need to do is draw a cut. And surprisingly, this gives you a conflict set. How does it give you a conflict set? Let's look at this blue one, for example, this blue line. To determine the conflict set, you look at the edges that cross the cut. So for example, this top one right here, it starts on the left-hand side and ends on the right-hand side. So I look at this edge, it comes from setting 1 equal to true, so we add that to our conflict set. Here's another edge that crosses the cut. It starts from 1 equal to true, So we include that in our conflict set. It's already there. Then you look at the next edge that crosses the cut. It starts from when we set 5 equal to true. So that's added to our conflict set. Here, from 3 equal to true, so that's in our set. And the last one is when 2 is equal to true. So by drawing this cut, looking at the edges that cross the cut, somehow, some way, we'll just treat it as magic, it gives us a conflict set. And now, you can trust me on this. This is saying, if we set 1 to true, if we set 2 to true, if we set 3 to true, and we set 5 to true, if all of those things occur, then this formula will never be satisfied. That's what a conflict set is. That's literally what I just explained it to you. So if we get that conflict set, that tells us the formula will never be satisfied, and look, it's a much deeper conflict set. We're not just looking at a clause and negating it. This is something we've discovered via DPLL. So if this is the case, if we say that, hey, we have this conflict set here, somehow we need to tell our solver we should never set 1 to true, 2 to true, 3 to true, and 5 to true. Because no matter what, that's going to cause an error. Okay. Implication graph. Draw a cut. So that way all of decision vertices are on one side, conflicts on the other. To get a conflict set, you look at the edges that cross the cut, see where they start from. And that somehow, some way, gives you the conflict set. Don't need to worry about how, we're just going to say it's magic later. So this is what I said. The conflict set is a subset of our current assignments. Once we have found a conflict set, or a subset of bad assignments, we never want to revisit this set of bad assignments in the future. So in our search tree, if we make our decisions, we reach a conflict, we get that conflict set 1, 2, 3, 5. We want to make sure as we continue exploring in hopes of finding a satisfying assignment, we never make these decisions again. This is something called clause learning. So it's a pretty big discovery, and it really enhanced the SAT revolution. And so, I don't like this. Essentially what we're going to do is, given a conflict set, we are going to add a clause to our original formula. So we start with some sort of formula here, phi equals blah, blah, blah. Oh, I should go the way around. So on and so forth. When we reach a conflict set here, we're going to go ahead, go back to our original formula, and add a clause that takes our conflict set and negates all of our variables. We're adding a clause because this tells us, hey, in order to satisfy this formula, which is our objective, we have to satisfy this clause, and the only way to satisfy this is if we never make these decisions again. So we're assisting our solver, saying, hey, don't make those decisions again. And that's done by adding that clause. So this is important. I will pause for if there are questions, but time is of the essence.
When we construct the DAG, there are multiple cuts we could make. So would that give us multiple conflict sets?
Yeah.
Okay.
So we find a conflict set, we add the clause, we continue to solve the formula, and we'll never make the same mistake again, hopefully. There's many conflict cuts. How do we decide which one to choose to build the conflict clause? We're calling this the conflict clause. And the answer to this is we want to add this clause, right? This is the mistake that we have made, mistake, right? We don't want to make this again. Adding the clause is one thing, but if we can somehow immediately learn from our mistake, that would be good. So in other words, we reach some point here, we're at this, we have these assignments. If we can immediately change something, that would be good. Well, that's not really well explained, but let's see, how can I explain this well? Ideally, we add a clause, we backtrack, or eventually we'll back jump, which will unassign things. If this clause, okay, God, I hate my life. This is why I hate this lecture. It's so stupid. When we're here, and we have this conflict set, and we add this clause, all of these are evaluated to false, right? That's literally what we just did. When we back jump, some of these things are going to get unassigned, right? The assignments we made at the decision level are going to be unassigned. Remember the green box that we repeated 16 times? That is what I'm talking about. Some of these things get unassigned. But if somehow we can make it such that only one thing gets unassigned after we back jump, like after we go back up here, then we can unit propagate on this and immediately learn from our mistakes. This is the most complex thing in the world. But Thomas, how are we going to be able to do it? I'm going to try to do it at 27 after. Can you pull up the pyramid? Oh, God.
We could skip the pyramid.
No, we're not going to skip it. So, are there just examples that I can show? That would be so easy. Okay.
Is it going to be like 4-1?
So here's what happens. We're going to choose a conflict set where only one of these things came from the very last decision level. If I look at 1, 2, 3, 5, the last decision level in our entire thing was decision level 4. Only one of these guys is at decision level 4. We're going to... Gosh, this is not a good lecture. Man. Okay.
Aren't 2 of them from 4?
How much time do I have? Thomas, should we skip the pyramid? Okay, let's just see. I have 7 minutes, I guess. Okay. This is where we at. Step 1, draw cut. Step 2, find cut where, or find, I guess we'll call this the clause, where only one vertex is at last decision level. As in, right here, right? Only 5 is at the last decision level. Step 3, look at the second largest decision level from our set, right? So 4 is the largest, 1, 2, 3, 5. 4 is the largest, 3 is the second largest, so on and so forth. So we look at decision level 3, and we're going to back jump to the second largest decision level. So this clause that we find is gonna do two things. It's going to allow us to back jump, and it's going to ensure that it's a unit clause when we do so. So this is a good cut because only one thing here is at the last decision level. The second largest decision level is something we call the asserting level, and that's 3. That's the second largest decision level.
By largest, do you mean like most nodes or like the greatest number?
Greatest number. Greatest number.
So what happens if you have like 7, 1 and then you have to back jump all the way up to like 1?
Say that again?
If like the conflict set was 1 and 7 and then the second largest is 1, so you go all the way back up to...
Shh, don't ask that question yet. Okay, other questions? Yeah, Robbie.
So in this example, if a cut only has decisions in it, if that doesn't have.
Yes, it happens to be, but as we saw, there's many different cuts, so it could have the assignment variables too. Yeah.
I guess why is that a good complex set?
Because only one of these thingies is at the largest decision level.
But why is that good?
Because now our rule says to back jump to the second largest decision level. So we back jump everything after decision level 3, the second largest decision level, gets unassigned. This was at decision level 4, that gets unassigned. It's a unit clause. We immediately learn from our mistake. Now, since it's unit, we're going to say set 5 to false. Like, make the correct decision this time. Is that here? Yeah, it's unit. So we change. Yes.
Is that not just what we were doing previously?
Isn't this just backtracking? Like, why did I waste your time and why did I waste my well-being, my mental health? Yeah. So.
Wait. Does that question just not get answered?
No, I'm going to answer it right now. I'm just thinking if I can do it in 3 minutes. And the answer is probably. So, I said that a good cut is something that has just one thing from the oldest decision level, which is true. But ideally, we want something more, right? If we use the proposed cut of here, after 1 and 7, right, that's a cut that works. We have one thing at decision level 4, and a different thing. Our asserting level would be 1, right? The second largest decision level would be 1. And so we would back jump up to that level 1. So now the question is, how do we figure out what's the best clause to add? That's why I had the flowchart. I'll show it to you later. Let's just answer this question and then do the pyramid.
What is this?
Here's what you do. Be quiet. Here's what you do. I hate this so much. You find the last decision you made, the last green node that you made, the highest decision level. And you draw paths to the conflict. You draw every single path from here to the conflict. Then you find the vertex that appears in every single path that has the highest timestamp. In this case, it's this vertex right here, because those are the two paths that exist. This vertex and this vertex appear in every single path, and this one has the highest timestamp. This is our special vertex. We call it the first unique implication point. And then you're going to draw your cut immediately after that timestamp. So everything t equals 7 and before will be on one side. Everything t equals 8 and afterwards will be on the other side. This is the ideal cut. It's the same thing, we just have a different conflict set. And then we follow us here. We have one thing from the current decision level, it being this guy right here. We look at the second largest decision level, which is 1. Is it a conflict clause? All right, yeah, that's the conflict clause, right? That's the thing we add to the formula. Is it asserting? Yeah, okay, you don't even know what that means. The asserting level is 1. We back jump up there. And then proceed as normal. It's pure mem. Questions while we prepare for the
Wait, can you
pyramid?
explain again how to do the cut?
Yeah. Do you understand how you find the unique implication point?
No.
Okay. To find the unique implication point, you start from the last decision vertex. In this case, 5 at 4.
I was at the last.
Because that's like the decisions we made are highlighted in green.
Oh yeah.
That's the one that has the highest decision level. You draw paths to the conflict vertex. You find the vertices that appear on every single path, and you find the oldest one, and then you cut right out.
Okay. Yeah. Wait, so you just go from that. You go from that vertex. You find the path to your conflict.
The unique implication point. It's t equals 7. Okay. You draw the line such that t equals 7 and everything before it is on the left side. Everything after t equals 7 is on the right.
Wait, so where does time come in then?
Time was when we created the vertex. Every time we created a vertex, we created this time.
No, I mean like where's it being used?
It's telling us where to make the cut.
Oh, okay,
The UIP, we look at the timestamp,
Oh, okay, got it.
cut right out.
All right.
What if there is no UI?
There always will be.
There will
It's
be.
just the first word.
Okay. Proof.